Hmm. Okay. Thanks, YouTube. I know I'm live. Okay. Actually, right. Okay. Yep, wrong button. So that works. And that works. Okay. Right. So today we're going to take a look at an actual algorithm again, because I decided to scrap last stream. Can peek at the result. It's gonna look like this basically. And I'm also going to explain the folding of a 2D array into a 1D array. I'm gonna start with that actually. So let's switch to Paint. Let's see if I can paint with the mouse. So if we have, right, let's look at the code actually, right? Where's the code? There's a code. So if we look at our maze, when we decided to model our, hi Howard, when we decided to model our maze as a 2D array, 2D array, right, as a matrix. I mentioned that we can also model it as a 1D array, and I got a question on Discord if I could explain how that works in a bit more detail. So we're going to start with that first, and then we're going to return back to mazes and Paint. So if we actually have an, our maze here, and we have a coordinate 0, 0 here, and then coordinates 1, 0, and then 2, 0, and I'm going to stick with 3. Then we have 0, 1, 1, 1, 2, 1, 0, 2. Sorry, I keep trying to flip X and Y, which isn't healthy. 1, 2, and 2, 2, right? So that's our 2D array, which we want to transform to a 1D array. So the basic idea is we take each row and just write them after each other. Here. So the result we get is then 0, 0, 0, 1, 0, 2, 0, 0, 1, 1, 1, 2, 1, 0, 2, 1, 0, 1, 2, god damn it, and 2, 2, right? That is this transformation. And the row transitions are here. So we need a method of actually computing our index, right? If we want to find, let's say, cell 2, 1 here, how do we actually find the cell? And we can do that by realizing that every row we placed here has the width of our matrix. Let's call it W. So to go down by a row, what we need to do in the 1D case is go right by the width. And then add on the x value to go additionally that amount. So the position of this index here would be equal to the x coordinate plus the y coordinate times the width. That's basically all we need to do to index into the 1D array. And we can do the reverse of this as well by simply taking the mod to find x and taking an integer division, not a floating point division, or rounding down, doesn't matter, to find the y coordinate. So this transformation we can do both ways, which is why I said it doesn't really matter which one we pick. The 1D representation has a few advantages over the 2D representation in terms of performance, because we have cache locality, etc., etc. I'm not going to go into any of that because it doesn't matter in our case at all. So I hope that makes sense. And that's set up. And then we're going to delete our algorithm here, because that's what I did last time. And we can quickly go over the changes. So I added a select here that allows us to choose between different algorithms later on, because we want to be able to we want to look at various different ones, and it's nice if we can just toggle between them. We're also going to add more options later on to, for example, show the texture, etc., etc. So if we look at this, now our maze is not very interesting. We're rendering a 25 by 25 here. I also added a random generator. I decided to just add a package, even though we could have just copy pasted some code, because we want to have the same maze every time we generate it and not a random one, because JavaScript random isn't very good. Right. So since my series already has the binary one, I decided to start with the Sidewinder. And the way this works is, pick up Paint again. Is if we have our maze, here, then for every cell, so we're going through this cell by cell, and for every cell we're going to decide either to go right. Let me pick a different color. That's a bad color. Either to go right or up. And we're going to bias it towards going right. So going right is much more likely. And what this will create is a lot of corridors, basically, that mostly stretch horizontally and sometimes go up. But when they go up, they stop going right. And that prevents us from creating a loop, which is the thing we need to preserve. Because if we recall a perfect maze, what we're trying to generate is a maze that doesn't have islands, and every point is reachable from any other point. By exactly one path. So there's no loops or cycles. And that's what we're going to do. So here's a comment I wrote last time, which basically explains the same thing. So for we can write our loop here for row in of, because it's JavaScript. And I need brackets for row of, let row of maze dot cells, and then for let cell of maze dot row. Decide direction to go. And there's a few special things we need to pay attention to. The first thing is, what if we are at the right edge, top edge, and then we're going to pick only the only available direction, which is either up or right. And if we are already at the top right corner, which is another special case, we do nothing. Nothing. Right. So we can declare a type here, because we know we have 3 options here. Let's call it none, right, and up. And the direction we're going to go for the cell, we can start off in none. And we can force this into type checking. And now we just need to decide the thing we want to know. So if cell x equals to the maze, x is the columns -1, that means we are on the right edge, then dir becomes up, potentially. We need to have another check here. And cell.y unequals. No, let's check the none case first. So maze dot rows -1. So we have the top left corner. And let's just do this, and then we can say dir is none. Then else if cell.x equals maze dot columns -1. And we could extract these, and maybe we should do that. Const is left as right edge. Which is then cell x equals maze columns -1 is top edge. Maze rows -1. And then we can simplify this down here and say is top edge and is right edge. Then we do this, and this reads much nicer as well. And then this becomes is else if we're on the right edge, if then the direction has to go up. We know we are not on the corner, so up is available. And else if is top edge, then we know we go to the right. And in all other cases, we do our random check here. So we can do if r dot float. We want the next float. And that is supposed to be smaller bias. So should have explained this before. The way this function is set up is we take in our random number generator columns, rows, and a bias. And this bias decides how likely we're going to go to the right. And that's it. So a higher number means we're going to the right more likely. Which means that if we are smaller than the bias, we are going to say the direction is right, and else our direction is going to be left, up. Now that we know which direction we go, we do car for path. So we can switch over our direction. That is not how you write case. Case up. Keep forgetting that you do it this way in JavaScript. Right, and none and default do the same thing. And that is nothing. That was the wrong direction on the insert. So, we want to fetch the cell above us and break down the wall in the north. So cell dot walls north equals false, and then other equals maze cells, first the y coordinate cell dot y, then the x coordinate cell dot x, dot walls dot south equals false. And we need to increment, so we want to go up, right? And up is, so top left is 0, 0. So up is going by -1 on the y coordinate. And then let's just copy this. I don't need to assign this. I can just do that. And instead of going on the y coordinate, we simply go to the right on the x coordinate. And then we return the maze. And ideally, this would work. But it doesn't. Where's my thingy? There it is. So if we reload this, we see it crashes out with cell y-1 is undefined. We need to figure out why that is happening. So let's go back and figure this out. So columns on the x. Yeah, we're checking the wrong edge. We want to know if y is 0, because as I said, the top is 0. And we still need to break the east wall, because we're going right, and the other, we want to break the west wall while we're at it. Okay. We transition back. We see we have our maze here. If we reload this, we're going to notice this stays the same maze, and that is why we picked a random seed, a seedable random number, because that allows us to debug should anything be wrong. Now, for those that were watched the binary tree generation, they realize that this is actually quite similar, except that there's no bias in the binary tree. We're picking 50-50 chance to go right or up, and that results in a binary tree. So implementing the binary tree for us here is super simple. We just pick our generate sidewinder here, and we just pick bias of 0.5, and we get our binary tree for free. Right, if I reload, I'm going back to the sidewinder, because that's not a state, not a path here, because it's not a router, etc. Maybe something to fix. So we have both the sidewinder algorithm and the binary tree, and now it would be nice to get texture. So I keep closing Paint. I don't know why I do that, because I keep needing it. There we go. Yeah, okay. So what does texture mean? We know we can create a maze, but we don't know anything about our maze. For example, if we look at our actual maze, we notice that the right corridor and the top corridor is always fully connected. So there's a pattern here. We also notice that if we follow a path here, that we're always going to the top right. So there's also a pattern here. And it would be nice if we had some method of visualizing such biases in our maze. And that's what we're going to try to do now. And the way we're going to do is we're going to color from some starting cell. So the color of a cell, okay, let me try to explain that. So we have a starting cell and we have a candidate cell. And the color of C is proportionate to the distance between S and C. And that will give us something we call texture. We're going to pick starting cell S by hover of a mouse. So if we hover over a mouse, we're going to get the texture. So first, let's set up the UI. And let's add a checkbox. Maybe. Show texture. And this is a checkbox. Input type checkbox. I believe like this, and then on change value dot target dot value, I believe. And then we want here a set show texture to whatever this is. And I hope this is right. It's been a while. Show texture. This is Boolean. And we're going to start off with false. And what's here? String. Input React get value. What do we actually get out of here? This is completely useless. Stack Overflow, I mean. So let's look at input on, oh, probably not sharing this. Okay. So I guess let's look at here input. Then is it just gonna output true and false as a string? Ah, we can just use checked, right? And let's just use that. Checked. And then since we have no algorithm to actually show our maze here, let's just output just a text here, show texture if our if we show our texture. Like so. Let's go back to our thing. And if we click it, we're rendering the text, and if we don't, then we don't. Which is what we want. So. I'm not gonna worry about formatting any of this. This isn't interesting. Let's actually figure out how to draw this. So we'll need to have another draw here. Similar to draw maze, but draw texture. So we can go to this. And I'm just gonna copy this entire function and paste it and call it draw texture. Or let's not call it draw texture, but draw texture. Let's call it texture renderer. Like so. And down here somewhere, we're going to draw the texture renderer as the second thing because we want it to be on top. Texture renderer for this. Let's just copy this line. Because it'll need the exact same parameters. So we get our paths here, and how does onHover behave with paths? I actually don't know. Does it actually detect the inside? We'll find out. So we don't actually want a stroke, which let's look up the path properties. Yada yada. Nothing interesting here. Stroke. Fills and stroke. Down here. Stroke opacity. That's the one we want. Let's put our... Let's do this backwards. Color, we're going to just do... Color doesn't matter. Because we're just going to set stroke opacity to... 0. There we go. Oh, I copied that. I didn't want to copy that. Yeah, I'm just messing it. There we go. I should copy this with a space. Sorry, still getting used to this thing. And where do we draw another color down here? And up here. I removed that from the... Okay. So we shouldn't be rendering anything anymore. But we're not actually... This makes no sense. We remove this, we remove that. We remove all of this. And what we want to do is actually draw 4 times. All 4 here. So we draw to here. Can we do commas? I don't know. But let's do a new line. Copy this. We move in the first one, but we don't move in the second one. So we draw a line to 0, 0, then we draw a line to... We don't do this. So we are, x coordinate is cell size, so we are not drawing on the x coordinate. We need to draw down now. Yeah, come on. Where's my and symbol? It's my dollar symbol. There it is. We're going down by the cell size. Then we're going left by the cell size. And I believe... Please stop. And I believe Z is close. And then we don't need any of this. And let's debug this by drawing it with red and put our stroke opacity to 1. No errors. And we are drawing something in red, which is good. I'm not sure why we're not drawing everything. So let's move this to the new line. So we're starting in the top left corner. We're drawing to the right by cell size. Then we're drawing down by cell size. Then we're drawing left by cell size. Why? We don't actually need this, because we're never using this. Oh, because we were checking for direction. Okay, that is much better. We are now drawing everything, and the fill is set to black, I believe, for some reason. But that's good. So, then we can fill this with color. And we're just going to we're just going to scale the opacity because it's it's simpler. It's not that. That's why maybe we'll do it another way. But this is max distance, and we'll figure out how to get them in a second. Divided by actual distance. Let's remove stroke opacity, set this to 0. This will crash if we do that, because actual distance can be 0. So what we actually want to do is actual distance by max distance. And then let's quickly define them here. Equals 1, and let max distance equals 1. Doesn't matter, just so that we have something. If we switch over, our eyes start burning. Why are we showing texture? Because I forgot to. Do this. Okay. Why is everything red? We shouldn't be drawing this. And our color here is white. Ah, because I flipped them. Whoops. Okay, this is draw maze. And this is texture renderer. We switch over now. Now, this makes much more sense. Okay. So, our texture renderer, I wanted to know if the on hover actually works as expected. Is there an on hover in React? I keep forgetting what they're called. React on hover. I guess on mouse enter and leave. That's just fine. So let's do on mouse enter. Whatever this is, event console log event. Does this work? Yes, because it was flipped. I apologize. I put the mouse enter and leave here in the hopes it does something. And I have the maze here in the hopes that we're going to get any sort of output here. But we appear to not get any. So, yeah, let's figure out how we do that. SVG path on mouse enter. Or mouse over or whatever. How does this help me? Oh, near. Which implies that this should work. Right? Yeah. Path, hover, and click. Well, that works here. And where do they have pointer events? Oh, that's not what we need. SVG path pointer events. It was with a mouse event, yeah. Do we see path in here? Well, we see polyline, so yeah, path is in here, good. And then value, bounding box, visible painted, visible fill, visible stroke, visible painted, fill, stroke. On the bounding box, well, no, we should use on the fill and stroke. Do we have... I don't want the bounding box. But since we are opacity 0, this would make sense. Because it's not visible. Well, let's just go for fill then. And what's this called? Pointer events equals fill. Let's see if that works. Oh, I should click on show texture. Maybe it would have worked before I never clicked on show texture. So we have an enter, we have a leave, which seems to work. Yay. Okay. I flipped the... I swear I will get used to this eventually, but we have our events here now. Sorry. Back to code. And then we've got that going, all of this going, this is fine. We want to know which cell we're actually highlighting, because we need a start cell of some sort. From cell, set from cell, su state. And we're going to use index. Going to use a cell here, because we don't have actually IDs. And we're gonna start with null. Cell or null. We start with null. Why is this red? Update import. And then if we do, and then we're going to compute our distances here, right? So we can do if actual distance, we can simply set to if from cell is null, actual distance is 0. Otherwise, we can set it to 1 for now. That allows us to test our hover logic. And here, instead of this, we're going to set from cell cell. And I'm not sure in which order they fire, which is going to be interesting. Which is why we're going to use the set from cell before, and then before equals cell. Then we're going to return null. Otherwise, we're going to return before. So since the problem we have potentially is that if we hover over a cell and we move out of it and move into the next one, I'm not entirely certain if in which order they will fire. If we leave first and then enter, or if we enter and then leave. Okay. I'm not sure what you want to tell me with weep, bro, but okay. So this makes sure that if we're getting called in the wrong order, we're not going to mess this up. I'm also not sure if this is the behavior across all browsers the same. And I don't know if this is deterministic or random in which order they get called. The set from cell we can call without any danger. Is that standardized between browsers, Daria? Or is that something we want? Anyway, we can see, we can at least detect if a mouse is in the, we can't see anything because I didn't switch again. So if I enter the area, if I then leave it, it flashes red. Yay. Now we need to do the hard part. And the way this works is we need to implement breadth first search, basically. So we can do this. No, we need to do this every time the from cell changes. So we can make this a function. And do compute distances. So. And then we have a map here. Distances. We're never gonna set this. And this is just going to be a record. String, I guess, to number. Oops. Like so. That is not at all how you write React. There we go. Let's define our function here. And let's do this even differently. We're going to go for cell. We're going to feed in the maze. And we're going to feed in the distances. Because we're just never gonna set this. Because I don't want to copy that over and over again. Function. Compute distances. First thing is the cell. Second thing is the maze. Third thing is the distances, which is the record string number. And we're going to mutate mutates distances in place. The proper functional way would be to return a new record here, etc., but we're not gonna do that. Because for large mazes, this could actually get expensive to constantly copy it over and over and over again. Let's make sure we are compiling. We are. And let's just compute random distances for now. So for no, let's just implement it properly, right? Okay. We also want max distance, so let's put this into the record as well. Distances max equals set maze time cells rows times maze dot columns. That is the absolute maximum you can have. And that's not gonna help us. We want it to actually set to -1. Sorry, I'm just thinking about which value. I nearly set this to 0, which would have crushed potentially the thing. So minimum distance, we can also just say 1, right? Then we avoid a potential 0. and we want to actually subtract this number from 1. The reason we want to do that is it doesn't matter. There's no reason. Not right now. We can flip how we paint it with a gradient later if we wanted to. But let's just get moving with this. So we have a queue, which is an array of cells, actually. And we have a function here that'll get us the neighborhood of a cell, because this is actually a set. No, it's a queue. And when we have a set visited, which is a set of cells. New set. Like so. Do we still need this function for the neighborhood? Let's do it anyway. And let's actually move this function not into here, but to wherever the maze is defined. And export function neighbors for a maze. Which is a maze. And we're going to return a cell array. So the results is an array here. We're going to return it. Sorry. So we want the left, top, right, and bottom cell if they exist. So we should also ask for which cell actually, right? Because, right? Do we want the cell or X and Y? Let's go with the cell for now. So we can do the same thing we had before. And that is we can copy the is right edge here is top edge. Actually, yeah, that is what we want to copy. And then we can do can paste this again and have is left edge and is bottom edge. And this time we have maze rows -1 and this is a 0. Right. Because we can now do simple checks. If we are the left edge, we know we're not going to add the left neighbor. Otherwise, we're going to add the left neighbor. So it's just simple, just if is not left edge. I called it results. Push maze cells cell dot y first, then x, And this is the left edge, so we're going to push the left neighbor. So we can do this. And let's copy this and paste this 4 times, and then we're going to check the right edge here. We're going to check the top edge. Bottom edge. Bottom edge means we're going +1 here. And top edge means we're going -1. And +1. And then we're going to return the results. That's the neighborhood. Okay, back to here. We'll need that function in a second. I defined it in advance. So the first cell in the queue is obviously the cell we started with. We already saw the cell, we don't want to evaluate it again. And then we have a while q brackets q length larger 0, our algorithm's gonna run. We need to still set the distance on our cell. So let's actually open this up again and go to our maze here. And I shouldn't call this types anymore because there's more than types in here. But so we have the neighbors and we want a ID of some sort. Export function cell ID. You're gonna take in a cell. You're going to return a string. And it's just gonna be cell.x cell.y. Because then we can simply do cell ID of cell equals 0. Because the starting cell, the distance from the starting cell is 0. We need to set up some variables. Let current be a cell. Let max distance be equal to 1. We don't actually need to do this. Do we need to set up anything else? No. Okay. So cell is going to be a q dot unshift, was it? No, shift. Removes the first element and returns it. Shift it is. We can also put an exclamation point because we know Q cannot be empty. We have at least one element in the queue because length is larger 0. Something TypeScript technically could know at this point. So we're going to look at the cell. We have our neighbors. which is our neighbors of cell, and we need our maze in here. And now for every member of this neighborhood, we're going to do something. So we're going to look at other of n. So in breadth first search, we're going to do two things. We're going to add, we're not going to process cells we've already seen, and we're going to add these cells. So if we've seen the cell, we'll do nothing. If we haven't seen the cell, then we're going to add it to the queue, set the flag that we visited it, and compute the distance for it, because the distance is going to be one further step. Now, of course, the neighbors are all neighbors, including the ones we can't reach. So we need to also check, is there a path, basically, on the neighbor? So I'm actually thinking that the neighbors here isn't quite right, the implementation. And we need to fix this. Because we don't want to know only if it's the left edge, but we also need to have a path. So let's say candidate equals this nonsense. And then if candidate dot, we don't need the candidate. We don't need this. We can check it on the same cell. And cell dot walls. So we're not the left edge, and we want to add the left. So which is the west one. So if we have not a wall to the west, then we add it. And we're going to do that for the other ones as well. This is the right edge, so walls east. This is the top edge. And this is okay. My keyboard switched language for some reason, and I switched it back. Why am I typing maze? I wanted to type cell. Walls south. And I need to negate this, right? Let's double check. Left, not left edge, and there is no wall to the west. So there is a path to the left. Right edge, and there is a path to the east. Top edge, and there's a path north. Not bottom edge, and there's a path south. Okay, that seems to check out. Okay, so now our neighbors actually make sense. And then we can do the thing we talked about. So if other in different language, if visited dot as, apparently. Other, if it doesn't have it, then we're going to do some work. First thing we're going to do is we set the distance on other. So distances, cell ID of other equals distances of cell ID of the current cell we're looking at. And my neighbors is still wrong. Plus 1. The this should be current cell, not cell. Oh, I called it cell here. Current. There we go. Make sure. Current is the unshifted one. We're getting the neighbors of the current one. Then we're going through the neighborhood of that cell. If we haven't seen that cell yet, we're going to increase the distance to the cell we are looking at of the neighborhood, plus 1. That is from the cell we came from. And we're going to add to visited other. Because we've seen it already. We don't want to add it again. We don't want to evaluate it again, otherwise we're going to run into an endless loop. And we're going to push this cell into the queue. And this is a breadth-first search, basically, except we don't have a target point. Usually what you would do is also check and if cell is end, and then you'd return. And have another here target cell or something that you want. And instead of distances, you would record from which cell you came, so then you can return the path. So this, I'm not sure why. Yeah, so this is more comparable to Dijkstra. What we're not doing, we should still update max distance. I've got a video on breadth first search, I believe. So I don't know if I want to explain it right now in more depth. I could, but I also feel like that's going to blow the intended 1 to 2 hours that I wanted to do. If there's a desire, I can do that next time. And we need to update max distances. Max distance equals math.max distance. And let's extract this. Still trying to remember keyboard shortcuts. And that is D, and D equals to what we just said. And then we can compare this to D. So if we, and then we can just set distance, and then we can just do this down here. Distance as max equals to max distance. Hi. That should work. Hopefully, possibly, maybe. We'll find out. We guarantee that max distance is never 0, so we're never dividing by 0. Let's add this as a comment. Max is reserved for max distance and is never 0. Do we need to clean up distances? No, maybe, possibly not going to. Okay, and then max distance is simply distances of max And actual distance instead of 1 is going to be distances of cell ID of the... That's not written here. That's written down here. The reason I use let instead of const is because I've been writing a lot of Rust, and that's the keyword there. So I just write let. No other reason. They could be consts. Doesn't really matter. Well, semantically, we're implying that we're ready to mutate this. Yeah. Anyway, so we should have texture in theory, possibly, maybe working. So we're going to show texture. Yeah, okay, so no, we're going to look at this, but so we have a nice gradient, and we can see that when we start somewhere, the distance scales nicely, and we see a pattern here, and that is that the cells right next to this are really far away. So high color difference between two neighboring cells means that cells are really far away. So looking at the texture of this thing, we see that if we look at the top right corner, we have a smooth gradient. So from the top right corner, every cell is roughly the same distance. But if we look at anything on the left or right corner, we see that the neighbors that we can't get to, there's a wall in between, are really, really far away. And specifically, the top ones tend to be further away than the bottom ones. And that's simply the nature of this algorithm. We prefer going right. That means going to the right is always shorter. Actually, not the top ones. The right edges here, sorry. The right edges are closer than the top and bottom ones. Don't know why I said left. Bottom one. Because we have a right bias, and if we go up or down, we are going to... that's a much rarer event. And if we look at the binary tree, we see a similar pattern. Top right corner, same thing. We would expect uniform distribution. But if we look at any cell here, and we see the binary tree nature much better, a lot better, with the texture, and that is the branches here, right next to the one we're looking at, are actually equidistant, more or less. And we see that it goes kinda in like a tree pattern. But we also see we have a very high directionality. You always just need to go top right to reach the top right corner. And ideally, so an easy maze is one with a lot of gradient, with a high distribution, a high contrast here, because that means we know a lot about it. On the other hand, if smooth gradients is we have no idea how to get to any cell, because this is the maximum difficulty, basically. Because from here, every time you make a decision to go down or left, because these are the only decisions you can make from here, you have no idea which direction's right. But to find the top right corner or any cell that is top right of here, you know you need to go top right. More or less. So, yeah, that's basically what it means. Let's fix this, because that's ugly. And that is because we set the distance to 0 here, and we shouldn't do that. We can just... We don't necessarily have computed this, so we should still do this. But we're just going to check in here as well on from cell. Actually, we don't need to do that up there. So if from cell is null, then our opacity is 0. Otherwise, it's going to be this division, and then we don't need this at all. We can just do this. And then we're going to get rid of our ugly thing. So if we toggle texture now, we're not going to do anything, but if we hover over anything, we can see the texture. Right. Trying to think about what else to do. Let's flip the... Do we want to flip? Let's pick a nicer color. Nah, doesn't matter. Whatever this color is. And hopefully that worked. I don't like that color. There are bright colors here. I don't know, like a nice toxic green. Much better. Okay. It's actually not better because of walls being white. We should pick a darker color. Sorry, showing the thing. Yeah, because... I guess we could render them in reverse order as well, because the opacity fills the... There we go. Okay. So I'm through with what I actually plan to do. So we can, if anyone has a question, we can address that. Otherwise, I'd stop here and say 1.5 hours are enough of me preaching at people. That's my champ book. Just waiting for the latency. Okay. Then I'll see you next. Okay. Good. Now there's actually latency is worse than last time. Let me check something. I mean, it's way too late for this, but Yeah, I didn't set it to low latency. Okay. Sorry. Right. Then let's see each other next time. Or not. It depends. Goodbye.